Hello everyone, this is Ugur. In this video, I'm going to present you a paper which appeared at the first ACM SIGPLAN workshop on machine learning and programming languages. I'm a PhD student at University of Maryland, College Park. There with my colleagues Parsa, Jeff, and Adam, we are working in a project whose goal is to use machine learning to distinguish the false alarms from the true problems that static code analysis tools report, so that we can filter out the false alarms as a debugging aid for developers. Towards this direction, this paper presents an initial case study in which we learn the classifier for the error reports of a static code analysis. Alright, in this talk we are interested in bug detection aspects of static code analysis, or SCA in short. It is a difficult problem that people have been working on for at least 5 decades. Now we have many SCA tools, and in practice, we often have some requirements for them. We like to have tools that are fast, scalable, and sound, meaning we expect them to find all flaws, not missing any. So the problem gets even harder with such requirements. Thus, many static code analysis tools make assumptions and approximations in the analysis, which in turn results in many false alarms that are distracting and wasting developers' times. Our goal is to distinguish and filter out these false alarms so that developers will not encounter them. In this case study, we are learning a classifier to do so. Given the analyzed code and the error reports, we formalize this problem as a binary classification problem with the classes true positive and false positive. We conducted a set of experiments in which we ran the Java static code analysis tool findSegBugs on OWASP benchmark test suite for SQL injection flows. In this dataset, roughly half of the error reports are false positive. To give you an overall view of the results, with the proposed learning techniques, we achieved 85% accuracy in classification and filtered 81% of the false positives without drastically affecting the true positives. Manually investigating why we achieved these good results, we observe that our learning algorithms are capturing some signals in the code that are indeed leading to false positive error reports from the SCA tool and for the dataset we used in this case study. We observe that these signals are explanatory rather than random correlations. Now I will continue with the overall workflow. In the existing scenario, there is source code which is analyzed using an SCA tool. The analysis results in a list of error reports. In practice, we observe that many of these error reports are false alarms. To distinguish them, we are introducing a couple more steps after the analysis and before showing the results to the developer. We take the analyzed source code and the error reports and do some pre-processing on them. In particular, for each error report, we do code reduction, simplification, and labeling. After this pre-processing, we have a dataset of reduced and labeled bytecode. In this dataset, each data point corresponds to one error report. Finally, we learn a classifier from this dataset using a naive Bayes model and an LSTM model. Now I will give you more details on each of these boxes, starting with the code reduction techniques. Looking at the bytecode of a class, we see that there are lots of things that does not matter for the error report. In fact, in general, only a small portion of the code is relevant for that matter. So, with the irrelevant parts in the code, data is noisy. Therefore, we do code reduction to remove the irrelevant parts. The benefits are we are avoiding overfitting the noise, speeding up the learning, and using a smaller amount of data. Okay, let's continue with the first code reduction technique that we call method body. Here, we just use the body of the method that has the error line in it. It is a very simple technique, but it misses the relevant code that is not in the body of the method, and it may include some irrelevant code which may be a noise. Therefore, the dataset generated with this code reduction technique will be a little coarse. Moving on, the second code reduction technique is computing the backward slice. A program slice is a subset of statements that affect the behavior at a particular point of the program. There are many kinds of it. In this work, we are interested in static backward slice. Starting from the error line, we slice the code backward up to the entry point. Here, we are again cutting down the code, but this time keeping more of the context that led to the error report. Therefore, resulting data will be more fine-grained. We used Voila program slicer from IBM T.J. Wasson laboratory. However, we experienced excessive execution times when computing backward slices, even for simple and short programs. To avoid this problem, we configured Voila to narrow down the scope and limit the analysis it does for computing the slice. More details on this is available in the paper. This is all about the code reduction techniques. After code reduction, we have further simplifications that happened before learning. But some of those simplifications are specific to learning model at hand. So I will jump over and explain the learning models first, so that covering the simplifications will be easier later on. Alright, first learning model is the naive Bayes. We opt to use this model because it is easy to implement and it enables us to find correlations in the dataset. We formulate the problem as computing the probability of an error report being a false positive given the underlying code. Here, code is the program analyzed. We unfold this formula using naive Bayes theorem as probability of code given error report equals being a false positive multiplied by probability of error report being a false positive divided by probability of code given the error report false positive multiplied by probability of being false positive plus probability of seeing this code in a true positive multiplied by probability of true positive. To compute these probabilities, we formalize the code as a sequence of instructions. Furthermore, we assume Markov property, which for this case study means that the probability of seeing an instruction is independent of other instructions. We acknowledge that this assumption does not necessarily hold for the dataset we have, but it enables us to have an initial idea about what is happening in the data. Our second model does not have this assumption. Finally, with Markov property, we can compute the probability of having this code in a false positive by multiplying the probabilities of seeing each instruction in the false positives. Alright, second model is the LSTM, which is a recurrent neural network with two recurrent connections that enables the model to capture long-term dependencies in the data. LSTM has been applied to many NLP tasks successfully, and we opt to use LSTM because our problem is similar to the sentiment analysis NLP task. Our data written is in a language, it has sequential structure, furthermore, it also has long-term dependencies. We used Ada-delta optimization algorithm which has adaptive learning rate. This figure shows the network structure unrolled over time. We have a single layer of LSTM, we feed the data points token by token and get an output value h for each of them. Then we do a mean pooling over these output values. Finally, we have logistic regression to classify the data points into one of the classes. This is all about learning models. Now I will continue with the further simplifications we did on an example program. This is a Java class with two methods, doPost and doSomething. doPost method takes an HTTP servlet request parameter. At line 4, we get all the values of the foo request header. Then at line 6, we read the first value into the param variable. Note that this is an untrusted source because malicious parties can leverage this to create a security threat for the system. Therefore, param variable is considered as a tainted variable at this point because the value came from an untrusted source. Then at line 8, param parameter passed as an argument to the doSomething method, which returns a string value read into the string variable bar. Bar is then concatenated into an SQL string to be executed on the database. The question is, was bar safe? Because if it is not safe, there is a potential SQL injection threat. Very simply, in SQL injection, malicious users manipulate SQL queries to perform operations on a database that they normally do not have access to. The answer lies in the body of the doSomething method. We see that the last value this bar variable gets is the value associated with key A, which was inserted into the map at line 16, and it is a hard-coded string, therefore it is safe. Therefore it is safe, so there is no possibility of an SQL injection. But running find checkbox for this code, we get an error report that is therefore a false positive. Alright, we get this sequence of Java bytecode instructions for the example program by applying method body code reduction technique. So all instructions here are in the doPost method, and we have nothing from the doSomething method. For training the naive Bayes model, we remove the gray part and only use the red part, which is basically just the Java bytecode instructions without any arguments, except the invoke instructions. With them, we kept the invoked class and method names. In addition to that, we treat all kinds of invoke instructions as same by replacing them with word invoke. Looking at the things we removed, first, numbers. We remove them because they don't have consistent meaning over all the dataset. Next, we remove string literals, project-specific class and method names, because we don't want to learn them as they are not generalizable. They don't appear in other projects. So with the Markov property we have, this data will be a bag of instructions without an order. For the LSTM model, we use more of the data. We keep arguments and return types of the invoke methods. We again remove the numbers, but instead of removing string literals and project-specific things, we replace them with words string and uncall this time. We think these differences are helpful in the LSTM model because here we treat each word as an individual token and data becomes a sequence of tokens we feed into the model in order. Whereas in naive Bayes, there is no order, we don't split apart the instructions or their arguments as we did in here. Next, the backward slice of the example. Note that this time we have instructions from both methods because they affect the behavior at the error line. Alright, for running the naive Bayes, we used only the red parts. In addition to the earlier simplifications, here we remove method names, line numbers, parameter indexes, exception indexes, so that what we fed into the model is very similar to the method body data point. For the LSTM model, we merged the class and method names into a single token, as in the first line. Rest is similar to what we explained earlier. Okay, now let's talk about the case study of SCA tool FindCheckbox. FindCheckbox is a plugin of Findbox checking for security-related flows. It performs taint analysis, which is a kind of data flow analysis. In this study, this study is only done for Java programming language, and we are focusing on SQL injection flows. As the dataset, we used OWASP benchmark, which is a test suite developed to evaluate the performance of SCA tools. In this test suite, roughly half of the test cases are real security flaws, and remaining half are safe, but they are designed to trick SCA tools raise false alarms. So ideally, a perfect SCA tool would emit an error report for all of the flawed test cases, but no error reports for the tricky test cases. This test suite helps us to mitigate the labeling task for this case study. because we know the error reports generated for the flow of test cases are true positive, and likewise error reports generated for the tricky test cases are false positive. Alright, running find checkbox on the OWASP benchmark just for the test cases exercising SQL injection scenarios, we got 2,371 error reports. Roughly half of them are true positive and remaining half are false positive. Note that by applying the two code reduction techniques, we have two datasets from these error reports. Now results. In all experiments, the data was randomly split into 80% training and 20% test sets. These matrices are computed using the test set. Furthermore, recall and precision are computed with respect to the false positive clause as shown in the bottom of the slide. In this table, first thing to note is that naive Bayes model works so fast compared to the LSTM. It completes the training in a second as opposed to 17 and 18 minutes of LSTM. But since the training is done offline and rarely 18 minutes is not a concern at all. Second, we see that LSTM classifiers have higher accuracy compared to the naive Bayes classifier. This is expected because there was more information available to them, and also LSTM is a more sophisticated model. Next, note that we prefer higher precision to higher recall because classifying real problems as false positives is very undesirable. For this reason, LSTM trained on the method body dataset is preferable as it has very high precision. But on the other hand, as we mentioned earlier, backward slice dataset has less noise and more relevant parts. Therefore, it is likely that the LSTM trained on the backward slice is more generalizable. Some more details on the findings of the naive Bayes model. We used a metric which we called false positive dependence, shown here. With this metric, we basically find the instructions that mostly appear in the samples of one of two classes. It ranges in between -0.5 and 0.5. The higher it is in magnitude, the more correlated the instruction is. Positive and negative values mean correlation with false positive and true positive classes respectively. Based on this metric, the most significant instructions are these three invoke instructions. Encoder invocations appear most in the true positive class, whereas array list and hash map invocations appear in the false positive class. Looking into the OWASP test cases, we observe that these collection objects are used to trick SCA tools into raising false alarms. Just like in the example code we have seen, a tainted value gets inserted into a hash map. Then because of that insertion, find checkbox assumes that the entire hash map is tainted. Clearly, this is an approximation which results in a false positive error reports. Likewise, encoder objects are used to confuse the SCA tools as well. So here we can say that the naive Bayes model is indeed learning plausible links in the data rather than random correlations. Lastly, note that the values are higher in the backward slice dataset, which means that the model trained on the backward slice dataset is more confident about these instructions. This is expected because this dataset has less noise and more relevant instructions. Probably this is also why this dataset led to higher accuracy. Alright, next I will give you some details on the LSTM model. Here we color the background of input tokens based on the output value of the LSTM cell for two example backward slices. The second one is the example program we discussed, which was a false positive. The first one is very similar to the example program, but it had a real problem, therefore a true positive. Here, yellow means negative, blue means positive, white means under threshold output value. First, let's have a look at the first tokens. Clearly, since there is no history before this token, this high negative output value is just due to this token. But this is not always the case. Thanks to the memory unit of the LSTM, output values are affected by a history of tokens. As an example, let's have a look at the last two tokens. return n. We see that they have the opposite meaning in these samples, which is clearly because of the history of tokens that appeared in the LSTM that LSTM sees in both samples. This shows that by capturing the dependencies in the data, LSTM is able to infer the context in which these tokens are appearing. Next, we see that LSTM finds many hashmap and encoder-related instructions to be interesting too. This is in accordance with the findings of our naive Bayes model and manual examination. Now, I'd like to mention about the threats to validity of this case study. We think that one of the biggest threats is representativeness of the dataset used. We acknowledge that OWASP benchmark test suite is not a good representative of real-world programs in many aspects like size and functionality. But despite that, this dataset is still a good starting point, helping us to demonstrate that the approach is promising. Next, we only experimented with one open source SCA tool for one pull-off type and for one programming language. We plan to address these issues in the future work. Conclusion. Right, we presented a learning approach to distinguish and filter out the false positives of SCA. We evaluated the proposed approach in a case study of FindSegBox in which we experimented with two code reduction techniques and two machine learning models. With the naive Bayes model, we discovered some plausible relations in the data, and with the LSTM model, we discovered 85% accuracy in classification. In the future work, we will generate a dataset of real-world programs with true positive and false positive error reports generated for them. We will conduct extended experiments with more advanced machine learning techniques. In particular, we are interested in recursive neural networks that can train on tree-structured input data. Lastly, we plan to set up this as a semi-supervised online service that SCA tool developers and users can benefit from. This work is supported by the Department of Homeland Security, and we like to thank our partners at UIPUI, Dr. James, Dr. Rajiv, Abhinadan, and Zach. Thank you very much for listening.